Hey, so for our last unit, Unit 8, we'll be covering Chapter 20 on electrochemistry and then 21 on nuclear chemistry. So, first starting with electrochemistry, specifically this field of study is really looking into the relationship between electricity and chemical reactions. So, when we think of electricity, if you're taking physics, you should think of like flow of electrons, and we know electrons are moving around in chemical reactions. So now we're going to really take an intentional look at this. So before we go into the actual chemical reactions, we need to be able to assign oxidation numbers. And in your last class, before me, which has been a long time ago at this point, you did learn about this. And it's pretty similar to what you've done. So for example, just as a preface, if I look at something like sodium chloride, I would assign the oxidation number for this, since it's in an ionic compound, as just the charge. So the oxidation number of sodium is going to be +1, and the oxidation number of chloride would be -1. We know that since it's a neutral compound, it needs to have its total. I won't even do some. The total of this whole molecule needs to equal 0. So if we add up the oxidation number of sodium, +1, with chloride, -1, we have 0. So that checks out. That's all we're going to be doing. Where it gets a little unfamiliar is when we have compounds that only have nonmetals, so we don't have necessarily charges, so those molecules, and I'll teach you the rules. So in general, if things are in their elemental state, so they're not charged, they have an oxidation number of 0. When we have an ion, so like for example, sodium here, +1, and chloride, -1, the oxidation number of that is just going to be equal to the charge. So these are really nice. When I have molecular compounds, so I'm thinking like all made up of nonmetals. So this could be polyatomic ions, right? Like NO3 -1 nitrate. It's made up of only nitrogen and oxygen. Those are nonmetals, so that would work. As well as actual compounds like carbon dioxide, CO2, it's just nonmetals. Then we are going to have some rules. So we give certain elements priority for their oxidation number. So if you see fluoride or fluorine in a molecule, we'll give it priority and it will have a charge of -1. If we don't see fluorine, but we see oxygen first, then we would give it a charge, an oxidation number of -2. If we don't have fluorine, we don't have oxygen in our compound, but we see hydrogen, then that's the first thing we see, then we'll give it a +1 charge. And then we'll base the other oxidation numbers off of this. So it's kind of a little bit of algebra here. And I'll give you a little bit more summary later. If you don't see any of those guys, but you see a group, the halide group, so group 7, then they'll get priority of having a -1. Oxygen's group, so oxygen and sulfur, -2, and then we'll have the nitrogen group after that. So if we get to there, I'll teach you that, but if not, I don't think it'll be super important. These are going to be the most common for priority. And then the last thing is, if our oxidation number of our total compound is if it's a polyatomic, so if I have a polyatomic ion, if I add up all of the oxidation numbers, then the total needs to equal the charge of that molecule or of that ion. If I have a neutral compound, then the sum of all of those oxidation numbers will equal 0, since it's uncharged. So that is something that hopefully you have learned, but maybe it's just been a minute since you've practiced it. So let's just practice here first. Let me erase this. Hopefully you wrote it on the side or something. So let's practice with this example down here. So I have zinc plus hydrogen chloride or hydrochloric acid, depending on the phase, reacts to form zinc chloride and hydrogen. So first thing I like to do is go through and identify the easy ones, and actually all of these are pretty straightforward. So do we have any elements? yeah, zinc is in its elemental phase, so we'll put 0 here. And then also hydrogen is uncharged. It's not an ion. Since these are ionic compounds that we have left over, we'll just identify the charge. So with HCl, we have hydrogen is +1 charge and chloride is -1. We should be really familiar with that with acid-base chemistry. And then zinc, we'll find it on the periodic table. It's an always a +2 charge. And then chloride, we have 2 of them. They're -1 each. So we don't do the total. We do what each chloride is. So chloride is -1. We have 2 of them. So we'll make sure that our total for this compound adds up to 0. So we have +2 and -1 twice. So that is good. Okay, so that is just with identifying oxidation numbers. Now, you have to do something with it. So we want to kind of keep track of what our oxidation numbers are doing. So for zinc, for example, let me do a little highlighter. For zinc, it went from 0 to +2. So we would say, well, I'll tell you the rule in a minute. And then we can see chloride, it stayed the same. It didn't do much. It went from, -1, and it's still -1, so nothing happened with that. And then lastly, our hydrogen went from +1 to 0, so it went down. So the rules are, if the oxidation number increases, we will say that element is oxidized. So we'll go see whose oxidation number went up from reactant to product. So we have zinc went from 0 to +2. That went up. So we will say that zinc is oxidized. We'll write that here. Okay. Now we could go if the oxidation number decreases, we will say that that element was reduced. And to me, this is what makes the most sense, because if an oxidation number goes down, we could also say another synonym for going down would be reducing. So if the oxidation number reduced, then that element was reduced. And that's honestly what I look for. I look for the element that decreased its oxidation number, and then I'm like, oh, that was reduced. Oh, it's reduced. So we would say that hydrogen here, it was reduced. So in order to be reduced, it goes from a +1 to a 0. So it had to gain an electron to balance out, or to decrease its oxidation number. So it gained an electron. And zinc had to go from a 0 to a +2. So in order to do that, it had to lose electrons. Just a quick thing just terminology. We would say that the thing that was reduced is called the oxidizing agent. Basically, because it was reduced, it caused the other thing to be oxidized. And we'll say that the zinc here, it was oxidized, we'll call it the reducing agent. Okay. Now, keep in mind that redox reactions, if something is reduced and something is oxidized, that happens at the exact same time. It's not like one happens and now it causes the other thing to happen. They have to happen simultaneously. So what this looks like here, if we look at this reaction, we have hydrochloric acid here with a piece of zinc metal. Now it's going to react. Hydrogen gas gets bubbled off, and all of that zinc metal dissolves into zinc ions. So definitely a reaction happened, lots of chemical changes going on. Okay, so now we're actually going to get into the chemical reactions. So when we do balancing these reactions, and you might think I already know how to balance a reaction. Well, sorry, these are extra complicated. So you don't know how to balance these kinds of reactions yet, but you will by the end of this lesson. So we want to identify the oxidation and the reduction, and then balance each one separately before bringing them together. Because not only do we have to balance mass, we also have to balance electrons being exchanged here. So for example, if I have tin 2 plus and iron 3 plus reacting to form tin 4 plus and iron 2 plus, if we just look at that, it looks balanced as it is. But in reality, it's not, because our total charges aren't balanced out. If we look at this guy over here, it has a total positive 5 charge if we add up those charges. And this one has a positive 6, so we're not balanced. And unfortunately, it's not as easy as just saying, oh, I'm going to throw an electron on one side. I wish. That would be nice. So we're going to go look and see who is oxidized and who is reduced. And when it's just ionic compounds here, it's kind of nice because the oxidation numbers are just the charge. So we have tin going from 2 to 4, and we have iron going from 3 to 2. So if you're me, I'm going to say, okay, who was reduced? Whose number went down? Well, I have iron goes from 3 to 2, so iron is reduced, which means by default tin is oxidized. And now that I've practiced this quite a bit lately, I'm getting familiar with recognizing that oxidation is an increase in charge, or oxidation number. So now I'm going to write out the reaction. So I have the oxidation is going to be tin 2 plus going to tin 4 plus, and I have the reduction is iron 3 plus going to iron 2 plus. So when we have these nice little simple reactions, and then you're maybe like, it doesn't look simple to me, that's okay. We will write each one separately. Then I want to balance the charges. So since my masses are equal, I have 1 tin on the reactants, 1 tin on the product. For iron, I have 1 and 1. So my masses are balanced, but my charges are not. So for tin, I have a +2 on the reactant side, and I have a negative, or a +4 here. So in order, I need to add electrons. So electrons, if you remember, are negative charge, so it's going to decrease the charge. So I'm going to put it on the side that has extra charge. So I'm going to put electron over here. In order to make sure we have +2 and +2 on each side, I need 2 of them. Cool. So now I'm going to do tin, or nope, I lied, iron. Iron has a +3 and a +2. So in order to bring down make the charges equivalent, I'm going to add an electron on this side. So now they are balanced in mass and also in electrons for each half reaction. Now before we could put them together, we actually have to make sure numbers of electrons match, so that way, kind of think of electrons as intermediates. So I have 2 electrons on my tin reaction, only 1 on my iron reaction, so I'm going to multiply this whole reduction reaction by 2. And then that's how we get our final reaction. So our electrons would cancel out here, and we'll get tin plus 2 iron 3s go to tin plus 4 plus 2 iron 2s. And now our electrons are balanced. So these types of reactions are kind of nice because we really only have to worry about balancing out those electrons. In some, and I'm going to give you the general layout of balancing these when they get more complicated. So when they're not just ions being changed into a new charge, we have a little extra steps. So I'm going to write these on the board for you so you'll have them when we're doing these practice problems, and you're going to want to bookmark this slide so you can come back to it and kind of be using it until you get familiar with it. So first thing we're going to do is we're going to, in our kind of skeletal reaction, we're going to just assign oxidation numbers to each element, and we'll figure out who is being oxidized and who is being reduced. Then you're going to write out your half reactions. So the element being oxidized is going to be 1 half reaction, and the next one is going to be, and then you write the reduced one. And so you'll want to also include electrons on this and charges. Now before we balance everything, we want to balance our half reactions by mass. So first you're going to make sure all of your elements are the same. You're going to balance any element other than hydrogen and oxygen. So balance elements other than hydrogen and oxygen first. Then anytime you see an oxygen after that, you'll write H2O. And then now we added some extra hydrogens, so we'll put in hydrogen where we need to balance that out. That should take care of balancing. The last step here is if you're doing this in a basic solution, then you're going to neutralize your hydrogens with hydroxides since you have an excess amount of hydroxides. And we know that that will end up forming some more waters. So you'll put hydroxides on both sides in order to balance out the hydrogen ion. Then we'll balance, once that is done. Okay, so already many steps here. So take a deep breath, and we'll do them step by step. We have your checklist. It's going to be fine. Then we're going to balance each of the half reactions. So we now want to make sure we have the masses done. We're going to balance these now by charge. So we're going to add up the charges on our reactant side and our product side, and then we'll add electrons in order to bring down the charges to be, or the amount of charge to be equivalent on both sides. Now we have our half reactions balanced completely. You're going to take a look at your oxidized and your reduced half reactions and make sure the number of electrons are the same. If they're not the same, then you're going to multiply by in order to get a common denominator. Now you are officially done. You just add your reactions together, and then if you have the ability and positive attitude to check your work, then you can. But if you follow this in this process, it should work out nicely. So starting off with an example, this one is not being done in basic solution, so we don't have to do that hydroxide step. So first thing we need to do is identify the oxidation numbers. So I'm going to move it down so I can have some space to write. So for manganese here, well, let's do any easy ones. So I noticed that manganese is an ion on the product side, so the oxidation number is +2. Now the rest aren't as easy, so let's start with manganese permanganate. So permanganate is MnO4-. So this is a polyatomic ion. So the total charge of this molecule total oxidation number needs to be -1. So we're going to write -1 equals, so manganese can have multiple different oxidation numbers, and if you look at our priority, we don't have a fluorine, and then oxygens after that. So we're going to assign oxygen a -2. So I have 1 manganese, and I'm going to add, I have 4 oxygens, and they're all -2. So now what I get is -1 equals manganese plus, we'll do -8, and then we'll add over 8 to both sides, and we get that manganese is +7. So I'll come over here, put a +7 on manganese, and a -2 on oxygen. Now let's do oxalate, C2O4-2. So we'll do -2 is the charge here, equals, so we have to, who comes first in priority? So we have fluorine, we don't have fluorine. Oxygen, oh, I have oxygen. So I'm going to solve for carbon, and I have 4 oxygens, and we give them a -2 charge. So we have -2 equals 2 carbons minus 8, so we'll add 8 over, and so I get 6 equals 2 carbons, so divide by 2. So carbon equals +3 here. Weird. So we have +3 here, and then our oxygen, -2. So our last thing is carbon dioxide. So we have CO2. Now it is neutral, so its total oxidation of the molecule will be 0. We have carbon and oxygen. We already identified that carbon comes after the priority for oxygen. So I have +2 oxygens, and there we give that -2 charge. So I have 0 equals carbon -4, so carbon equals +4 here. And oxygen is -2. So we're going to go identify our oxidized and reduced. So remember, who goes down? That's our reduce. So manganese goes from +7 to -2. Oh, that's a drop. So here is our reduced. And then we have oxygen, -2, -2, -2. Nothing happened with oxygen. Carbon, +3 to +4. Oh, carbon went up. Carbon is oxidized. So what I'll do is I'll write my oxidation reaction, which will just include the carbon components. C2O4 2- goes to CO2. And then I have reduced is going to be manganese oxide, just -1, goes to Mn2+. So manganese goes from +7, so carbon goes from 3+ to 4+, and manganese goes from +7 to +2. So first we're going to start out by balancing the carbon. So let's do the oxidized reaction. So we have C2O4 2- goes to CO2. So first thing we're going to do is balance our elements that are not hydrogen or oxygen. So that leaves carbon. So I have 2 carbons on my reactant side, only 1 on the product side, multiply by 2. Now my elements are balanced. Carbon and oxygen are balanced, so I can actually just be done now with the balancing of elements. Now I want to balance charges. So I have a -2 on this side from this charge and a neutral over here. So -2 and 0. So in order to get balance, I need to add electrons. Well, adding electrons are going to bring down my charge. So I'm going to add 2 electrons here to bring me down to -2. So now this one is done. So now we're going to balance the manganese. So we have MnO4- goes to Mn2+. So I have 1 manganese on this side, on the reactant side, 1 on the product side. Cool. So now let's balance the oxygen. So I have 4 oxygens on the reactant side, so I need to add 4 waters over here. Okay, well now I added too many hydrogens, so I have 8 hydrogens, so I'm gonna need to add 4 hydrogen ions over here. So now that is balanced with mass. Oops, I lied, not 4, I need 8 because I have 8 over here. So now I'm balanced with mass, so now I need to balance charge. So I have a -1 and then I have a +8. So my total charge on this side is +7. And then I have a +2 here, and I have 0 here. So my total charge is +2. So I need to add some electrons. So in order to bring down my charge on my reactant side, I'm going to add 5 electrons. Now I added 5, -5, and so I'm at +2, they match. Cool. So now the last thing I have to do is make sure that my amount of electrons are the same for both of my half reactions. So on my carbon, I have 2 electrons, and on my manganese, I have 5. Those are not the same. So the first number that they both go into is 10. So I'm going to need to, I'm going to rewrite it, multiply my carbon by 5, the whole reaction, and multiply my manganese by 2. So I get 5 C2O4 oxalate goes to 10 carbon dioxides and 10 electrons. For manganese, I'm going to multiply by 2, so I have 10 electrons plus 2 permanganates plus 16 hydrogens goes to 2 manganese ions plus 8 waters. Okay, so now that I'm done, I can add those reactions together. So I'm just going to write all of the reactants on one side and all of the products on the other. So all of my reactants from oxalate, is 5 C2. We need space. So 5 oxalates. Cool, that's all my reactants. Now I'm going to need to add all of these reactants. Plus 10 electrons, plus 2 permanganates, plus 16 hydrogen ions. Cool. And I'm going to react now to put all my products. So I have 10 carbon dioxides and 10 electrons. And then I have my products over here, 2 manganese ions and 8 waters. So let's cancel out some stuff. So first thing to notice is that our electrons cancel, which is what we were aiming for. And then honestly the only other thing to do here, actually that's all. In some situations you might have hydrogens or on both sides or waters on both sides, and so you'll want to kind of get rid of any extras. So consolidate. And now our final answer is 5 oxalates react with 2 permanganates and 16 hydrogen ions to go to 10 carbon dioxides, 2 manganese ions, and 8 waters. Okay, much longer than just balancing reactions, regular reactions, but this is how we balance a redox. Okay, so now we're going to practice the same thing, but now in a basic solution. So the only additional thing to do is add hydroxide when we're balancing out mass. And technically, you don't have to identify who's being reduced and oxidized in these steps. So let's just jump into the balancing part. If you want to go over the oxidation state numbers, then let me know. Let's jump in by balancing this first cyanide reaction here. So I have cyanide goes to this cyanide ion. Cool. Carbons are balanced, nitrogens are balanced. So the only thing here is that we don't have oxygen on the product side, so I need to add a water over here. So now my oxygens are balanced, but I have too many hydrogens, so I'm going to add 2 hydrogens over here. Before I do anything else, I'm now going to realize that I'm in basic solution, so I'm going to neutralize all of my hydrogens with hydroxide. So I'm going to I have 2 hydrogens, so I'm going to add 2 hydroxides to this side and 2 hydroxides to this side. You have to be even to keep that mass balanced. So what I get is cyanide plus water plus 2 hydroxide go to this ion, plus when we mix those together we get 2 waters. So we get 2 waters. Now notice that I have a water on this side and I have 2 waters on this side, so in reality this one's going to go away and one of these will go away. So we have 2 minus 1 basically. So that is our reaction there. Cool. Now we need to balance electrons. So I have -1, -2 here. So I have a total, so -1, -2, a total of -3 on this side. I have -1 over here, a neutral. So I need to add 2 electrons over here to balance that out. Great. So now we're going to work with our permanganate reaction. So I have manganese or permanganate goes to manganese 4 oxide. So my manganese are balanced, but I have 2 oxygens on my product side, 4 on my reactant side. So I'm going to add 2 waters over here on the products to balance that out. Now I have too many hydrogens. I have 4 hydrogens, so I'm going to add 4 hydrogens on my product side. Cool. Now my masses are balanced, but I'm in basic solution, so I'm going to add 4 hydroxides here and 4 hydroxides here to both sides. Now this makes 4 waters. So what I get is manganese permanganate plus 4 waters on the reactant side, 2 waters on the product side, so I end up left with 2 waters total here. So 4 minus 2. That's going to give me manganese 4 oxide and 4 hydroxides. Last thing is charge, so I have a -1 from permanganate, neutral, so I have a total of -1 over here. I have neutral for manganese oxide and -4 from hydroxide, so -4 over here. So I need to add electrons to my reactants, 3 exactly, to get to -4 on both sides. Okay, now before we can add them together, we need to make sure that they have the same number of electrons. So write this in red. So I have 2 electrons on the cyanide, 3 electrons on the manganese. So I'm going to multiply this cyanide one by 3, and I'm going to multiply my manganese one by 2. So let's write those out. We're going to have 3 cyanide plus 6 hydroxides goes to 3 CnO minus plus 3 waters plus 6 electrons. And then for manganese, I have 6 electrons plus 2 permanganates plus 4 waters goes to 2 manganese oxide, plus 8 hydroxide. So what can we cancel out here? So I have 6 electrons, perfect. Now I have hydroxides. I have 8 on this side and 6 on this side. So what's going to happen is that's going to go away, and we'll end up getting 2 left over on our product side. So let's actually just start adding things together. So I have 3 cyanides. My hydroxides cancel out here, so I get 2 hydroxides on this side. Okay. Permanganate, I have 2 of those. And then water, I have 4 waters on this side and 3 waters on this side. So these are all going to go away, and we're left with 1 water on my reactant side. So check, 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 done. Now I have my hydroxide is done, the electrons are done, so I have 3 of this cyanide, oxyacid, or oxyion, and 2 permanganate, or manganese oxides. Okay, and that's it. So, I know, many steps, but this is our end result. So now to practice for you, this one's a little bit more straightforward. Hopefully it's kind of a boost. You'll practice at least one of those other ones on a homework just to practice all of those steps. So let's, for this one, I do want you to actually identify the reduction and oxidation, which should be pretty straightforward. So remember, all neutral molecules are 0. This one's +2, aluminum's +3, copper's +2. So whose oxidation number goes down? Well, it looks like copper goes from +2 to 0, so we can say that copper is reduced. And then aluminum goes from 0 to +3, goes up, so we'll say aluminum is oxidized. So now let's write our reaction here. Aluminum goes to aluminum ion, and then we'll have copper 2 goes to copper ion, or copper metal. So let's start with aluminum. Aluminum is balanced. There's no oxygens in here. That's nice. And we're going to, now we can balance charge. So I have a +3 on my product side, neutral over here. So I'm going to add 3 electrons to my product to cancel out, and we'll be at 0 on both sides. Copper has a +2 and a 0, so I need to add 2 electrons over here to get them to be a neutral on both sides. Now I want to combine these reactions, but before I could do that, I need to make sure that my electrons are the same number. So I have 3 and 2, so I'm going to multiply this whole thing so that we have 6 electrons. So I'm going to multiply this side by 2, 2, 6, and multiply copper by 3. So 6, 3, and 3. Now we can add these together. So we're going to get our reactant, so 2 aluminum plus, so there's our only reactant here, 6 electrons from here, and 3 copper ions go to our products, 2 aluminum ions plus 6 electrons plus 3 copper metal. So we will cancel out our electrons and we get our balanced reaction. So we get 2 aluminum plus 3 copper ions go to 2 aluminum ions plus 3 copper metal. Okay, hopefully this process is a little easier to follow since we don't have any oxygens and hydrogens to balance out. When we have reactions, redox reactions happening in electrochemistry, we have electrons being transferred, and when that happens, energy gets released, specifically in spontaneous reactions. When those spontaneous reactions happen in electrochemistry, these are set up in voltaic cells. The energy that gets released will be able to do work if we have the system set up to a device that requires energy. So this is kind of like a battery system here. So we have, here we have a voltaic cell, okay. We have this bridge here that separates one side, so your oxidation happening on one side, and then your reduction happening on another side. So oxidation is going to happen at the anode. So anodes have anions attracted to it. So remember, oxidation has it where we have the oxidation number increasing. So a lot of times that's when we have something like a metal, let's say zinc, going to the ion. So our anode would be made up of zinc, and in our solution, when the reaction happens, zinc ions would go into solution and we have cations formed. Okay. Now reduction happens at the cathode, and it's called the cathode because it has cations attracted to it. So here's our cathode. Let's say this was copper. We would also have copper ions in solution here. And then we have copper here. So what would happen is when this reduction, we'll have reduction happening, so copper ions are going to plate onto this copper rod here, this copper electrode. So we're losing copper ions in solution and they're forming copper metal. When it does that, we end up getting a net amount of anions in solution. Now the anions from this side are attracted to the anode, and the cations that get formed on the from the anode get attracted to the cathode over here. So now when we do this, I'm having a net amount of, so I'm taking copper ions and I'm putting them into copper metal. And this is a barrier right here. So basically what I have now, I've gotten rid of some of my positive charge, so I get net negative charge over here. So in order to balance it, we need a salt bridge. I'll show you a salt bridge on the next slide, what it looks like, which is like this U-shaped container that connects the two sides and are able to make sure that charges are balanced. So the salt bridge would throw in some, once that positive charge gets taken out, it'll throw in some extra, like sodium, for example, that's not going to react, and it will help balance out that charge. And on this side, where we have our cations being formed, well, it'll throw in some anions on this side to balance out those charges, so we don't like have some electricity happening here. Because what happens is when we take our metal from our anode and put it into solution, what we're putting in some cations, so the electrons that got removed go up through the wire and into the cathode, which helps our metal ions here get reduced. Okay, it's a lot to take in, so I understand that's going to be a little complicated, and that's normal. So you'll take some time to practice this. Okay, cool. So, and then we can measure our electron flow through a voltmeter, or we could even hook up like a light bulb in here, and we'll see that it would turn on because we have electricity flowing. So so this is an example of having a salt bridge. So we have our anode and our cathode in separate beakers here. So here I have zinc and copper, just like I was saying. Metal is our electrodes. And then I have zinc ion in solution here. And I don't need very much and because it'll actually be being formed. And then over here I do have a decent concentration of copper ion because I need those copper ions to react to get reduced to form copper metal. So on our anode here we have zinc, and then that gets oxidized to form zinc ions that go into solution. And then here I have my cathode is copper, and those copper ions in solution, I need a good amount in solution so I can reduce them and they go on to the cathode. And keep in mind our actual electrodes are solid materials. I like this image because it really shows like on the scale of what's happening. So our zinc here is a metal solid, right? When it gets oxidized, it turns into zinc ions. When that happens, the two electrons that get removed, so these are our products, these ions, zinc ion and two electrons, the two electrons flow up through the electrode through the wire. Now they come over here to our cathode. Those two electrons are going to meet up with the copper ions in solution to form copper metal. And that's where our reduction is happening. Now, because since these are specifically separated, I'm going to get a net amount of zinc ions here, zinc 2+, and I'm going to be losing copper ions here, so I'm going to get an extra amount of negative charge. So I have extra positive charge from my zinc, extra negative charge from my lack of copper. So what happens is my salt bridge has potassium nitrate in it, and the nitrate is going to go into my anode container, and my potassium is going to go into my cathode container to help balance out that charge so we don't build up a huge amount of charge. The notation we use to kind of identify what's happening in our voltaic cell, so you don't have to like write a whole paragraph, is you write the anode and the cathode. Those are going to be on the outsides. These are your solid materials. So I would write zinc here for my anode, zinc solid, and I write a line. Then you write the electrolyte that's in the anode container. So in here we have zinc metal turned into zinc ion. So I'd write zinc 2+ aqueous. Now I write two lines here to indicate that that's the end of that electrode, that side of the voltaic cell. It could also mean salt bridge, it's kind of like now there's a separation. Now we write the electrode in our cathode container, so that'll be copper 2+ aqueous. Oops. And a line that indicates now our cathode, which in this case was copper metal. So that is how we write our notation. When we have this reaction happening, now I mentioned earlier that a voltaic cell happens spontaneously, so we're going to have electrons going from high potential energy to low potential energy. Okay, so they're stabilizing. So our high potential energy is at our anode, and it's flowing down into our cathode, these electrons. When we have this flow of electrons, this is a potential difference, right? The energy difference here is related to the amount of energy that we have, and we call this either electromotive force or EMF or the cell potential. I like cell potential because it makes more sense to me in terms of electricity. The units for this are volts. Keep in mind that a volt is a joule per coulomb, so an energy unit per unit of charge. These are all of these cell potential values can be found in a table you'll find on the next slide. So just like Gibbs energy and enthalpy and entropy, these are all tabulated data. So it'll tell us, okay, if I have copper ions getting reduced to copper metal, and that would take 2 electrons, then that has a certain cell potential. That has an energy associated with it. Okay, so that would be for this reduction. I'll actually call it the potential, the reduction potential. If I have the reverse reaction happening and I have copper turning into copper ions, then that would be the oxidation potential. And so these are all tabulated in our books and online. And just like when we had with entropy and enthalpy and all of that, we had something to compare it to. So for enthalpy, we compared to everything in their elemental states. We called all of those 0, and we compared everything to that. For entropy, our theoretical value was a perfect crystal at 0 Kelvin, and that was our 0. So just like that, we have a 0. And that reference here is for the standard hydrogen electrode. So standard meaning at 0 or 1 atmosphere and 25 degrees Celsius and 1 molar. Those are our standard conditions. Now for this, so when hydrogen is our electrode, and what we do is we take hydrogen ions and reduce them into hydrogen gas. We call this cell potential 0 volts. Okay, so we give that a 0. So the reduction is 0, the oxidation is 0. Basically, hydrogen is our 0 point. And everything is going to be compared to that. The table that we're going to reference is going to be reduction potentials. So for these situations, we're only going to see the reduction side of a reaction. Now in a redox reaction, we have reduction and oxidation happening. So instead of keeping tables of both oxidation and reduction, which would be the same thing just in reverse, we keep just the reduction potential. But I do want you to keep in mind that if I switch and I have, let's say I go, so here in this example I had a copper ion going to copper, it has a reduction potential of positive 0.34 volts. Okay. Now if I wanted to write it in reverse and I have copper metal being oxidized to form 2 electrons plus copper ion, so that's oxidation, the oxidation potential would be negative 0.34 volts. So when we flip the reaction, we just change the sign. In a little bit, we're going to see the table that has all of the reduction potentials, and we can kind of compare it. But before we do that, I want to kind of go over a little bit more about what this all means. So when we have a large cell potential, that means that reaction has a strong tendency to happen. So when we have really large values, then that reaction wants to happen. Okay, so large cell potentials really have a preference. If you remember learning about activity series, this is related to that. So when we have these cells connected, our half cells connected, and we have our voltaic cell, electrons are going to flow such that the reaction that has a higher cell potential is going to kind of be the one that dominates. So it happens so that the electrons flow, like we said earlier, from the anode to the cathode. So when we look at a chemical reaction and we notice, okay, we identified the thing that's being reduced and the thing that's being oxidized. If I go and look at the reduction potential of the thing that's being reduced and it has a really big positive number, then that means that it would like to be reduced. If I look at the thing that's oxidized and on the reduction potential and it has a really big negative number, then we're saying, okay, it likes to be oxidized because it does not want to be reduced. So this is a favorable reaction. That's going to happen. So let's look at these different reactions here. I have the zinc being oxidized to a zinc ion and copper being oxidized. So let's look at the oxidation potentials. Now, if just as an FYI, if I wanted to see the reduction potentials, it would be the opposite. So if I go look at the table on the next slide, the reduction potentials for these things will just be the same number but opposite sign. So I'm just writing that just for like FYI, just how we're seeing it. So zinc has a really positive oxidation potential. So that means it likes to be oxidized. Copper has a negative oxidation potential, which means it does not like to be oxidized. If we do the flip thing and just look at the reduction potentials, we can say, okay, zinc has a negative reduction potential, so it does not want to be reduced, which is what the oxidation potential told us. And then we can look at the reduction potential of copper, and it has a positive value, so it does like to be reduced, which validates our earlier statement about it not wanting to be oxidized. So when we have this, we're going to look at the table. When we see elements that are on the top of the table, the reduction potential table, that means that they have a really positive number. They like to be reduced. At the bottom of the reduction table, these are going to be elements or reactions that have negative reduction potentials, which means that they do not want to be reduced, they want to be oxidized. So positive reduction potential means likes to be reduced. Negative reduction potential means it likes to be oxidized. And we're going to actually compare those two to find out if a reaction is going to happen spontaneously. So you guessed it, we're going to end up going back into Gibbs free energy and connecting these two eventually. So here's our table. Sorry that it's sideways. I wanted to give you the most space on your slide. So we look over here at these electrode potentials. Now these are again reduction half reactions. So when they're up here, they're positive up to hydrogen, right? Here's hydrogen being reduced. And remember, that's our standard 0. Okay, so all of these ones above here, they are preferred to be reduced. Now all of these ones that are negative, they prefer to be oxidized. If I was to flip the table upside down, and I would have the oxidation half reactions, then all of our oxidized ones would have positive values, and that would show that they prefer to be oxidized. So instead of having to deal with thinking about flipping half cell reactions to have oxidation or not, we're just going to deal with this one table. So I know this is a lot today. The beginning is kind of rough with balancing those reactions, but I think as we continue through, it gets a little bit more straightforward.